All right. Hi, everyone. Once again, my name is Jordan Tweedie, and thank you again for the introduction. Thank you all so much for coming to listen to my seminar today. I'm really excited to share with you guys what I've done and what I've found so far with my research. So in this presentation, I am going to be discussing some of the impacts of assimilating unmanned aerial system or UAS data into the National Severe Storm Laboratory, the Experimental Warn-on-Forecast System, or WoFS. So this is what my master's thesis research focuses on, and I'm currently in the process of analyzing preliminary results. So I still have a ways to go in terms of making sense of all the data. But again, I'm excited to show you guys what I found so far today. So diving right into the motivation, since we are in the boundary layer seminar, I hope that everyone is familiar with the atmospheric or the planetary boundary layer. But for those of you that don't know, the atmospheric boundary layer, or the ABL, is the lowest part of the atmosphere that's affected by planetary surface conditions and characteristics. And this is where daily weather happens. So it's very important to understand the processes that are occurring within this layer. Despite this, there is still a lack of spatially and temporally high-resolution observations of the lower atmosphere, and one of the most common instruments that's capable of sampling thermodynamic and kinematic variables in the ABL is the radiosonde, which lacks spatial and temporal resolution and can also be quite costly. These are often only launched twice a day, sometimes more for special weather sounding. They're spaced out across the United States, and when there's helium shortages, we know that this can be an issue. Fortunately, over the past 10 years, increasing amounts of studies have shown successful experiments utilizing the assimilation of UAS data into numerical weather prediction models. And that being said, I do want to make it clear that I'm not recommending eliminating the use of radiosondes. Rather, these observations in conjunction with UAS data and other ground-based profiling systems can help to make these models and forecasts that much stronger. So because of this, there is an increased interest in assimilating UAS observations into NSSL's Experimental Warn-on-Forecast System, or WAS. Excuse me. And for those of you that are unfamiliar with WoFS, this is an ensemble data assimilation and forecasting system designed to provide 0 to 6 hour probabilistic guidance of severe and high impact weather events. So for my thesis, I chose to analyze the EF4 Rolling Fork tornado event that occurred in Mississippi during the late hours of March 24th, 2023, so almost a year ago now. This tornado was part of a larger severe weather outbreak that lasted from March 23rd to 27th, in which a mid-level trough was quickly moving eastward towards a strong upper-level high that was situated over the southeastern United States. This led to the formation of a strong southerly or southwesterly low-level jet that ejected warm, moist air from the Gulf of Mexico into an already unstable air mass located over the ArkLaMiss region. And the FCC issued a moderate risk with a 15% hatch tornado risk over the ArkLaMiss region in the day 1 Convective Outlook. This then led to the third mission of the PERiLS 2023 campaign being initiated, and the PERiLS campaign sought to characterize near-storm environments and storm processes of tornadic QLCSs. And so this was a successful deployment. We were able to have a full armada pretty much go to where the center, where the moderate risk was centered in this region. So we were able to have a lot of instrumentation deployed for this weather event in particular. At the same time, WoFS was also able to run a real-time experiment centered over the moderate risk area. So these are a few of the reasons why this was presenting to be a good case to analyze. So here I just want to show you guys a quick diagram of the National Weather Service's depiction of the EF4 Rolling Fork tornado track. This tornado touched down at 0057 UTC and remained on the ground until 0208 UTC. So this was a long track of violent tornado. The tornadic supercell that produced the Rolling Fork tornado, it actually went on to produce 2 EF3 tornadoes across Mississippi throughout the evening. So again, this was a very powerful supercell, and it was able to keep regaining energy to produce tornadoes throughout the evening. For the purpose of this study, again, we're only focusing on the Rolling Fork tornado because this was closest to where we gathered our observations. Also, time-wise, this was closest to our observations. And the EF4 Rolling Fork tornado, unfortunately, was the deadliest in the region in the last 50+ years. But the one good thing about this is that we were able to at least gather valuable scientific data from this event. So hopefully we can learn something from this and, of course, improve the forecasting so that these events become less deadly in the future. So moreover, this event was sampled with 3 UAS CopterSonde instruments in addition to other instruments during the PERiLS 2023 field campaign. The CopterSondes were placed at 3 stationary profiling sites that are shown here as the 3 red stars. I apologize, it's a little bit hard to see on the screen. The CopterSondes were located, there was one site in Lake Village, Arkansas, one was located in Piney Creek, Mississippi, and the third was located in Slaughter, Mississippi. The NSSL mobile sounding platform was also stationed where the blue triangle can be seen on the plot, And this is just northeast of where the Rolling Fork tornado touched down, which is depicted by the purple diamond in this figure. So the CopterSondes were collecting observations every 15 to 30 minutes from 1700 to 0000 UTC, with increased cadence closer to the arrival of storms, or they were getting closer to the actual profile of the site. And these sites were all co-located with the FCC's Day 1 Convective Outlook moderate risk, and thus the center of the WoFS domain. So pretty much everything was centered right on top of each other, and the Rolling Fork cell pretty much moved into the perfect environment for us to sample. So the mobile sounding system, which collected observations roughly every hour from 1700 to 0200 UTC, was able to launch its sounding approximately 7 minutes before the tornado touchdown, which is pretty impressive in my opinion. And since the mobile sounding data is not assimilated into WoFS, this is able to provide a means of observation verification, which we'll get into a little bit later. But just wanted to let you guys know we're only assimilating the UAS data. We're not assimilating any of the soundings. So furthermore, the Rolling Fork tornadic supercell makes a good choice for a case study because the WoFS domain was centered over the Rolling Fork tornado. The tornado moved through the UAS domain outlined in the pink triangle here shortly after touching down. And the observing platforms collecting data leading up to, right before and after the tornado were able to successfully collect this data. Therefore, my advisor and I are working on conducting observation system experiments to analyze the impact of assimilating the UAS data into the Warn-on-Forecast system. And these experiments include the control or the baseline Warn-on-Forecast system, as well as the Warn-on-Forecast ensemble with the addition of UAS observations. So we have our control run, and we have our run with the UAS assimilation. The baseline WoFS ensemble assimilates conventional observations such as mesonet data, in addition to radar observations and other conventionally normal meteorological observations. But again, no soundings are assimilated and no UAS data is assimilated into the control run. So truly the only difference between the baseline WoFS control run and the UAS WoFS run is just the assimilation of the UAS data. So we're able to see the direct impacts of assimilating those variables. So moving on to some more details about the actual Warn-on-Forecast system, for those of you that are not as much involved in the world of data assimilation. It is a WRF-based ensemble data assimilation and forecasting system designed to provide 0 to 6 hour probabilistic guidance as high impact and severe weather events, such as tornadoes, hail, excessive rainfall, and much more. We're constantly working on trying to develop new applications for the system, which I think is great. And the domain currently covers a 900 by 900 kilometer area with 3 kilometer horizontal grid spacing utilized for this experiment. A lot of experiments nowadays with WoFS are utilizing 1 kilometer grid spacing and even sub 1 kilometer grid spacing. But for the purpose of this experiment and just the timing of when I came to OU to start this project, we decided to stay with the 3 kilometer horizontal grid spacing. There are 50 vertical levels on a hybrid coordinate system that is roughly terrain following in the lower levels and pressure following in the upper levels. And a localization radius of 200 kilometers was utilized for assimilating the UAS data in this experiment. And that will be important and come into play a little bit later in this presentation. I'm also only examining the first 18 out of 36 ensemble members, primarily to conserve computational power. The second half of the 18 members are very close to what we see within the first 18 members, so we're kind of able to disregard them for this experiment. And the ensemble common filter data assimilation system assimilates observations every 15 minutes. So it's a continuously updating and cycling DA system. So 0 to 3 hour forecasts are launched every hour from 1700 to 0000 UTC, with output being binned every 5 minutes. This makes it really nice for analysis. And aside from understanding how the Warn-on-Forecast system works, we of course also need to understand how the use of the CopterSonde was applied in this study. So this is kind of the start of the show. The UAS instrument that was utilized for this experiment is the CopterSonde, which was designed by scientists here at the University of Oklahoma. Thank you to Dr. Tony Segales, Dr. Tyler Bell, Dr. Smith, and everyone else who works with BLISS. They have helped me greatly in learning all about the CopterSonde and how to really use and apply this data. So thank you for that. The CopterSonde collects data at a frequency of 10 hertz with an ascent speed of about 3 meters per second. And with sampled averaging, this results in observations gathered approximately every 3 meters or every 1 second. And this is great for high temporal resolution, or excuse me, high resolution temporal observations. So the CopterSonde gathers thermodynamic and kinematic information from the ABL, including temperature, dewpoint temperature, and horizontal wind speed and direction. And the observation errors for the CopterSonde measurements are quite small compared to other instruments, at least from what I've seen in my analysis. However, the CopterSonde does tend to underestimate high wind speeds when hitting its maximum threshold, which we'll discuss a little bit later. This might be the cause for underestimating wind shear and other related forecasting parameters. But again, further work is needed to confirm this, and I don't want to state that as a fact right now. So here you can see the time height diagram of the CopterSonde observations that were actually collected from 1700 to 0 UTC on the night of March 24th, going into March 25th when the Rolling Fork tornado occurred. And the CopterSonde collected ascending profiles of temperature, moisture, and wind data every 15 to 30 minutes. Despite entering the evening hours, we're actually able to see a slight increase in temperature in the lower levels of the atmosphere, especially at the Piney Creek and Slaughter site. This is prior to approximately 2300 UTC, and it's depicted by the orange shading in the top row of the plots here that you can kind of see at the bottom. Looking at the dew point temperature, most profiles remain under 65 degrees Fahrenheit or about 18 degrees Celsius prior to about 2200 UTC, after which there is a noticeable increase in moisture, especially at the Piney Creek site. And this can be seen by the increase in green and yellow shading in the second row of plots, especially here towards the end of the Piney Creek site. Additionally, the decreased heights towards the end of these profiles reflect the development of the strong southerly and southwesterly low-level jet over the sampled region. And this occurs because the CopterSondes have a built-in fail-safe mechanism that triggers the CopterSonde to land when it encounters the maximum wind threshold, which I believe is around 25 meters per second. So essentially, as the CopterSonde is ascending, if it hits a wind speed that is too dangerous for it to operate, it triggers itself to automatically come back down and land. So again, there might be an underestimation of some of these maximum wind speeds when it is hitting that threshold, but again, we're still working on this, looking into it, and I know that some new algorithms are currently being developed to try and calibrate for this too. Additionally, the shift in zonal wind is from mostly eastward to neutral to slightly westward, revealing the more southwesterly component of the low-level jet, and the meridional wind in the fourth row reflects the strengthening of the southerly low-level jet. Here, it's essentially positive Z winds heading northward the entire time, and we can just see it getting stronger, and also stronger winds reaching lower levels of the atmosphere as the evening goes on, which is the development of the low-level jet. So these trends are useful for understanding the differences in forecasts between the baseline WoFS and the WoFS run with UAS data, because they allow us to understand how the model is attempting to better fit itself to the observational values and trends. We're going to see this here in a few upcoming plots, but keep in mind all of these trends in the data that we're seeing here within these time height diagrams. This is essentially what the WoFS model is trying to push its model state base towards these observations in the UAS run of the WoFS ensemble. So getting into some more results here, this is a baseline WoFS sounding initialized at 1645 UTC and valid at 1700 UTC. The sounding itself is zoomed into the lower levels of the atmosphere from the surface to 700 hectopascals, while the photographs in the table represent the full vertical profile of the atmosphere and still give us some accurate data. The WoFS ensemble means are represented by the fixed solid blue and red lines, whereas the WoFS individual ensemble members are represented by these thin blue and red lines. And the PERiLS mobile sounding observational values are also notated by the dashed green and pink lines that you can see here. I apologize, it's a little bit hard to see. One thing I'm actually working on right now is trying to make this graph more legible. So if anyone has any recommendations afterwards, please, I'm more than happy to talk to you about it. Moreover, I would also like everyone to recall that the PERiLS mobile sounding was located in between the Piney Creek and the Lake Village sites. So I had to interpolate the WoFS data to that location. And looking at the photograph also, the thick rainbow line represents the WoFS mean, while the skinny gray lines represent the individual members, and the thin rainbow line represents the mobile sounding observations. Speaking back to what I just mentioned about interpolating the data to the PERiLS mobile sounding location, the reason that this is important is because this does lead to some minor differences in the forecasts. But here, compared to the WoFS run with UAS data, the plots are almost exactly the same, which we should expect to see for this initialization time. There are bound to be minor differences due to the interpolation calculations that I had to utilize, but these plots show us that before any UAS observations are assimilated beginning at 1700 UTC, the forecasts are nearly identical. So again, going back and forth, they look almost the same. This is before any UAS observations are assimilated into the UAS run. Good, this is what we like to see. Now here we see the baseline WoFS sounding initialized at 1700 UTC 15 minutes later and valid at 1705 UTC, similar to the first sounding plot. Since the first data assimilation cycle of UAS observations began at 1700 UTC, we can see the available soundings from two UAS profiling sites valid at 1700 UTC plotted in bright green dotted lines. I apologize, I know this might be a little bit hard to see. Again, this is something I'm trying to work on making a little bit more legible, but here we have these bright green lines. These represent the UAS CopterSonde profiles, which are a bit lower than the rest of the profiles that we see. Again, just because of the maximum wind threshold that they often hit. They also can't pass through clouds due to issues with moisture affecting the sensors. So for reasons such as this, we have to make sure that the UAS are not able to go up too high, and of course with FAA regulations too. So that's why these profiles are a little bit more limited. And we also have the temperatures. It's a little bit harder to see. It is plotted in some varying shades of pink and these dotted blue lines or these dotted pink lines here. But most of the temperature plots actually land on top of each other, so we won't be focusing on those ones as much. But again, focusing here on the UAS observational values. Again, this is interesting to see because we're only assimilating data from 2 spots. So we're not expecting to see very dramatic impacts on this forecast, but it is interesting to see that just with the assimilation of these 2 sites, there is a dramatic difference between the baseline WoFS and the WoFS UAS run. So looking at the run with the UAS data, we can see a clear impact from the addition of the UAS observations. Despite there only being data available again at 2 of the 3 profiling sites, this was enough to actually decrease the dew point temperature by 3 degrees. This in itself was actually able to eliminate a moist bias and actually create a dry bias within the WoFS on-level forecast. And this actually persists throughout most of the forecasting period, which we'll see in a couple of slides. This is most likely a result of assimilating significantly drier dew point temperatures at each of the UAS sites compared to MOL sounding sites. Again, you can see here these green lines are located significantly farther to the left than compared to the PERiLS mobile sounding observation in the dark green dashed line. So again, just showing that at the PERiLS site, it was a good bit drier there than it actually was at the PERiLS mobile sounding observation site. So we can also see that compared to the baseline run, we can see how the model is trying again to fit these observations closer to assimilated observations. And there's also a decrease in shape that we notice, as well as a slight decrease in low-level storm relative helicity and shear, despite the slight increase in low-level wind speeds. And this can also be seen in the lower levels of the photograph. There's also an increase in the LCL, the LFC, and SIN. However, most values in this table are actually now closer to the observational values. So just looking at the after the first cycle of data simulation, we can see that from the baseline WoFS to the control WoFS, from the baseline WoFS to the WoFS with the UAS assimilation, we can actually see the UAS data does help to correct the WoFS profile to be more in line with the actual observed value. So this is good to see for the beginning. Now, moving forward to the baseline WoFS forecast initialized at 000 UTC and valid at 0050 UTC, which was 7 minutes before the Rolling Fork tornado touchdown, we can see a large change in environmental conditions. This is to be expected. This was over a period of a few hours, and this was during the rapid onset development of supercells and tornadoes in the area. So we can see that the curvature of the photograph has increased, the dew point depression has decreased as the environment has significantly moistened and slightly warmed, and the lower level wind shear has also increased. The Cape values have also increased, while the SIN values have decreased, further reflecting the instability of the environment. And overall, the main takeaways from this are that, in my opinion, this is a really good loaded gun sounding. Based on soundings I've looked at before, this is pretty classic for a tornadic supercell, and so this makes sense when looking at it. So comparing the baseline WoFS to the UAS run, the sounding forecast actually appears to stray further from the mobile sounding observational values for the most part, which is interesting to see towards the end of the forecast period. Here you can see the blue line. It actually begins to shift further away from that dark green dotted line of the observational values. So a drier atmosphere is depicted here in the lower levels, again, potentially as a result of assimilating the drier UAS observation prior to 2200 UTC relative to the PERiLS location. The LFC has also ascended a bit in this run, but as long as it remains under 2 kilometers, it is still supportive of tornado genesis, which is good to see for a case. A slightly more eastward component can also be seen in the wind barbs closest to the surface, and I believe that this is further evidence of CopterSondes being able to more accurately capture the low-level jet that was contributing to correcting the location of storm tracks that we'll see in 2 plots. Also in the UAS run, the photograph features slightly less low-level clockwise curvature, but there is slightly more wind shear in the lower levels closest to the surface according to the table. So a little bit of mixed data here that's still requiring some further investigation. And again, while the UAS sounding appears slightly less conducive to tornado genesis, the typical forecast parameters of composite reflectivity probabilities and opaque vertical vorticity and more reveal a different story in terms of how the forecasts perform. So here we see the 15-minute forecast of 9-kilometer neighborhood ensemble probabilities and composite reflectivity greater than 40 dBz. And the Rolling Fork storm is depicted by the black MRMS 40 dBz contour located within the green circle. So the figure on the left is from the current baseline or control WoFS experiment, and the figure on the right is the result from assimilating CopterSonde observations, in addition to all other weather observations that we routinely assimilate into the baseline WoFS. So compared to the control run, the UAS experiment does a slightly better job of co-locating composite reflectivities in accordance with the location of the rolling fork supercell, as we can see here. And I do want to note that it is still important to look through the individual ensemble member composite reflectivities in order to understand how the actual storm structure is changing in each forecast as a result of the addition of UAS observations. Just looking at the neighborhood ensemble probabilities of composite reflectivity, this gets pretty, as you can see in the diagram, pretty well smoothed over, and it can really smooth over a lot of finer details that might be important to pick up on when looking at these individual forecasted numbers of reflectivity and storm structure. For the sake of time, the 9-kilometer neighborhood ensemble probabilities still provide valuable insight, fortunately, into the difference in these experiments. And more specifically, the composite reflectivity contours in the baseline lofts are shifted northeastward, which could be an indication of a placement or timing error within the model. This could also be reflective of the lack of an eastward component in the low-level jet not being captured by the baseline lofts, which could cause the storm to drift further northward. This is currently a hypothesis that I'm testing. Again, I don't want to make any claims that this is actually what's happening as a result of the UAS observation, but so far this is what the data has been pointing me towards. So looking at this diagram, you can see the 50-minute forecast of ensemble mean MLK at the 100 hectopascal level. The rolling fork supercell is depicted by the black MRMS azimuthal wind shear contour in the top of the green circle. I apologize, a little bit hard to see there, but it's this top one up here. And this green circle encompasses an area south of the storm in the inflow region, where compared to the baseline experiment, the UAS experiment increases the MLK. And we can see that here in this increase in the orange shading here. So I believe that the UAS observations are helping the model to better capture the extent of the southerly influx of warm, moist air from the Gulf of Mexico, especially after 2300, which contributed to higher MLK values in this region. And I also believe that the UAS data helped to better limit the previous convection in the model so that more instability and energy in the form of CAPE could be available to the rolling fork supercell as it propagated into the ArkLaMiss region. And again, this is really important where this CAPE is located because this is all in the southerly inflow region leading into the rolling fork storm, and especially with the southerly, southwesterly low-level jet that's ejecting in a whole bunch more moisture and warm air. That's really going to matter to the storm inflow region. So this is interesting to see. Additionally, the idea that the UAS observations help the model to conserve available potential energy for the rolling fork storm. It's further supported by some other swap plots that we'll be looking at. But again, more work is still needed to verify this hypothesis. So here, this is the 1-hour forecast of ensemble 90th percentile 0 to 2 kilometer vertical vorticity, which is a good proxy for mesocyclones within the loft ensemble. And the red triangles represent National Weather Service tornado reports during that 1-hour forecast period. I do want to note that typically it is better to use the azimuthal wind shear contours in order to determine the actual location of the tornado track or the rotational track. This is something I'm actually still working on currently, is coding up these plots and adding those overlays. So for the time being, this is why I chose to use the red triangles to represent the National Weather Service tornado reports instead. So here we can see that the placement of the lower level vorticity swath is closer to the location of the rolling fork storm in the UAS experiment here on the right, while the control run swath is displaced slightly southwest over here. The baseline loss also depicts the rolling fork storm as starting off strong and then tapering off, becoming weaker, whereas the UAS run reveals the opposite, where the rolling fork storm starts off weaker and then continues to go stronger throughout this forecast period. I believe that this could be due to the way in which the CAPE and instability are being modeled in these runs in combination with the increased eastward component of wind captured in the UAS run, which could possibly be helping to keep these tracks in the UAS run tilted a little bit more eastward that are veering off to the north. But again, still working to analyze this. So looking another hour into the forecast, we can confirm the continuation of the previously observed trend. The baseline loft vertical vorticity swath has mostly tapered off and strayed to the north, while the UAS experiment's vertical vorticity swath re-strengthens in accordance with tornado reports and remains tilted eastward, which again is what we like to see for the UAS run. This pattern makes sense based on what was observed in the 50-minute 100 hectopascal MLK forecast, and it has also been identified in a few other forecast parameters not pictured here just for the sake of time. Additionally, although it's not directly related to the rolling fork storm, I did want to point out that we can see that the other storm tracks to the north and the south of the rolling fork storm within the UAS run are actually tamped down a little bit more correctly in accordance with some of the tornado reports also. Again, we're only focusing on the rolling fork storm, but this is interesting when considering the localization radius of 200 kilometers that was used for this study. And this is one of the reasons why we're considering possibly trying a smaller localization radius to focus the impacts more so on the rolling fork storm and less on other surrounding storms and possibly areas where the observational values are going to be quite different from what we're assimilating into the model, for instance, what we saw with the UAS and the PERiLS observations. So overall, the UAS run does perform better at forecasting for the rolling fork tornadic supercell, and there are no dramatic changes to forecast, again, since we're only assimilating from 3 sites. If we were assimilating from a whole bunch more sites with a whole bunch more time, we would likely see a much more dramatic impact. But it is still interesting to see the impacts that are noticeable, just with even assimilating from only 2 sites at a time. The confidence, track, and intensity of the rolling fork storm are all improved with the addition of the UAS data. But the contradictory sounding plots where the UAS run strays more from observations than the baseline WoFS, that still is going to require further investigation. That's something that my advisor and I are currently looking into to try and see why this is actually happening. Because these sounding plots contradict a lot of the other forecast parameter plots we're seeing that do support the idea that the UAS run might have a little bit more valuable insight into predicting these tornadic supercells. So ultimately, I do believe that the UAS observations help to limit a moist bias in WoFS by reducing the northward spread of moisture from the Gulf of Mexico, correct the location of storm tracks by better detecting the near surface westerly component of the LLJ, and sustain the intensity of the rolling fork storm by more accurately estimating the amount of available energy in the environment in the form of CAPE and other variables. However, more work is still needed to determine the UAS observations' impact on WoFS modeling of the storm structure and evolution, and I am still continuing to go through all these analyses. So as for future steps, I'm continuing to work on investigating the different dynamical processes that are occurring within the storm inflow region in both experiments, as well as the contributing factors leading to the differences in desounding and hodograph plots, like I previously discussed. I'm also going to examine in more detail how storm structure and evolution is modeled differently in both experiments by looking at the individual ensemble members, like I also previously mentioned. And time permitting, my advisor and I are hoping to run another set of experiments, again with a smaller localization radius, to see how this impacts the UAS WoFS forecast. So ultimately, this could be especially helpful for determining at which vertical levels data is needed to help models resolve boundary layer processes, and especially when considering further experiments that we could do with this work. There is an idea that future studies could assimilate additional data from other ground-based observing systems, such as from CLAMP2, which is the collaborative lower atmospheric mobile profiling system, which includes various types of useful ground-based instrumentation. And further experiments utilizing study could also include a data denial experiment in which you only assimilate one of the UAS variables that's been observed, for instance, only observing temperature or only simulating temperature, only assimilating dewpoint temperature, only simulating horizontal wind speeds in order to actually determine the effects of each individual variable on the forecast. So again, this could all be really helpful for determining the ways in which not just UAS data, but also other ground-based profiling systems could be better assimilated into these models. This is a really exciting time where we're having a lot new innovations in ground-based observing systems. And so I think this is a really great time to really try and understand the best way to assimilate this, the best way to assimilate this data into the models that we're currently working with. So after acknowledgements, before I finish off, I just wanted to quickly thank the NOAA Weather Program Office for their funding for this project, as I likely would not be here without them. I also want to thank my advisor, Dr. Nusrat Yussouf, as well as Dr. Yuping Wang, Tyler Bell, Tony Segales, Liz Smith, and everyone else who has taken the time to teach me throughout this experience. Another big thanks to my friends and family for putting up with all of my rambling about this research over the past couple of years. And of course, I have to acknowledge my 3 fur babies that made sure I will never work alone, even this morning when I was practicing this presentation. So with all of that being said, I'll be happy to answer any questions, and thank you all so much. Mm-hmm. Mm-hmm. Yeah, and so that's actually something that and thank you for bringing this up. I did not mention this earlier, but when we're assimilating the UAS observations into the WoFS system, they're actually they're being assimilated to only certain vertical levels that were predefined. I believe that was set up by Dr. Yuping Wang before she was my predecessor on this project. And essentially, I believe that we are assimilating the UAS observations every 60 meters from 0 to 200 meters, and then it's every 100 meters above that. So I know that the data is being sent when it's actually being assimilated into the Warn-on-Forecast system. For the purpose of the sounding plot, I did not send the data just because I was trying to get an idea of a look at the raw plot. But yeah, sending the data, I'm curious if adding that in implementation of the sounding, because that might actually help to kind of correct a little bit of what we're seeing. But yeah, thank you. Mhm. Yeah. Mhm. Yeah, definitely. Yeah. Thank you again for the input. I appreciate it. Mhm. That is something that I am still trying to look at right now, looking at the storm dynamics, especially kind of looking at the evolution of the storm inflow region. That is something I am still not honestly 100% sure on. I'd probably have to talk to the science and consult with her a little bit for answering that. But yeah, I was gonna say it's still a little bit hard to determine what exactly is different in terms of the factors in terms of like the storm dynamic processes leading into the evolution of the rolling fork storm. But yeah, that is something we will be looking into. Yes, it was at 1700 that we began. Mhm. 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 And that's something I was kind of wondering about too. And just full transparency, my advisor, Dr. Nusrat Yussouf, she was actually the one who ran these data assimilation experiments herself. So she was the one in charge of setting all of the input variables and whatnot for that. But that's something that we were talking a little bit in one of our meetings earlier, a little bit, just trying to kind of overcorrect how the model is overshooting with the assimilation of UAS observations. Yeah, definitely. Yeah, for sure. Thank you. Yeah, here I was gonna say so. Okay, I was gonna say I'm pulling up my presentation again just because I know uh I had the errors listed in here. I have to make sure that's yeah. Yeah, so for the uncertainties that we're including, these are all as for the observation errors at least, these are standard, these are just statically set. Again, this is based off data that we were previously given from Tyler and a few other people within Blitz when working on assimilating this. Again, this is the way that the observation errors, the uncertainties, all of that stuff, that was all calculated actually before I came into the picture and began working on this. So I am still working, to be completely honest, on my understanding of how those uncertainties are calculated and how they're actually factored into the assimilation system. But yeah, that is something I'm still trying to understand. So thank you. Are there any other questions? Mhm. Mhm. Mm-hmm. 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 No, I completely agree with you. That was, again, was something that my advisor and I were just discussing last Friday too about that. So yeah, I completely agree with you on that. Mhm. Mhm. Yeah, so that is something, some of the previous works that I've looked at, some of the primary examples I've been given, they've been all very different types of environmental conditions and setups. Quite a few of them have been, I know, studying like downslope and upslope valley winds. There was another that was more so focused on convective initiation, which is relatively close to what I'm trying to do. That study I think was by I believe Dr. Junjun, who a few years ago, but that study is, I'd say, the closest to mine that I found. It's just kind of tricky. A lot of these UAS experiments seem to be very specific to the geography and the location in which they're being deployed. And so again, kind of looking at the different localization rating, this is something that I think could really open, like, could be a really interesting area of research, is looking at how UAS observations are assimilated in different, not only just different areas, but depending on the different environmental conditions too. Because I've seen quite a wide range of results across some of the papers. I think mostly positive, but again, just the way in which these are all getting assimilated, it seems to be pretty dependent on the local factors whenever these studies are being conducted. Yeah. Oh, that's tough. Mm. I think honestly, and this is just my opinion, I'm not sure if it's the most accurate or not. I think that having spatially more of the UAS sites, I think would be more impactful, at least in terms of the data simulation, just because you have more observational points that you're comparing it to. We only have 50 vertical levels, especially when interpolating that gets a little bit wonky and sending the data. But when looking at, I don't know, looking at that horizontally, since WoFS is 300 by 300 grid points, if we're able to add as many CopterSondes or as many more observational points as we can, like in terms of the horizontal surface, and I think that definitely could be helpful. As for the deeper profiles, of course, I mean, that would be great to see. Um, that's something I think I would honestly, I think having a larger number of profiling sites, even if it's at a lower elevation, I think would be more beneficial just for the data assimilation system.